go. Let's go ahead and go live. Okay, hi everyone. So back for another episode of Science and Technology Q&A for kids and others. And I see there are still some questions left over from last week. There's one from Rios asking, is the number 0 a natural number or just an integer? Well, usually when people say natural numbers, they mean numbers 1, 2, 3, 5, and they don't include 0. 0 has a very weird history. You know, we think of 0 as being a pretty natural and obvious concept today, but for a long time in the history of people doing calculations and math, 0 was an extremely unfamiliar idea. And people made all kinds of weird mistakes and so on as a result. Like I think the Romans didn't have a concept of 0. Their number system just firmly started at 1. And so when they had to do calculations for calendars, for example, where it was important to just say things start at the beginning of the year, they had some whole elaborate way of dealing with that, and they managed to get it wrong. And when first they set up what's now called the Julian calendar, it's not the calendar we use today, it's the calendar that was used in up to the 1500s, some places 1600s, some places a little bit later than that. But it was a calendar which added, I guess it added the month of August, if I remember correctly, named after Augustus Caesar, I think. You know, they added months to try and keep the time it takes the Earth to go around the sun aligned with the actual length of a year in days that they had worked out. And that's why we have leap years and things like that, is try and deal with the fact that the actual time it takes the Earth to go around the sun is not 365 days, it's 365.2481, I think, days. So in other words, but in any case, the Romans didn't have all that stuff straight, and they didn't have a notion of 0, and that caused their whole calculation of calendars to get extremely confused. And I would say the notion of 0, I mean, I think there's early evidence from, I think there's an early thing from Cambodia, some early things from India about people noticing the idea of 0. But I think the idea of 0 as something that was a serious number that you could think about was something really of the probably 1400s-ish time frame that became started to be really understood. I mean, nowadays it's kind of obvious. You're just counting numbers down, and you get you know, you get below 2, 1. What's next? Well, there's just 0. Then there's -1, et cetera, et cetera, et cetera. That wasn't obvious to people for a long time. You could do that. People would say there is no notion of 0 because it's nothing. So it was very, very confusing. In fact, back in, when was it, around 1500, I think, a guy called Cardano was much responsible for, strangely, at pretty much the same time, really taking negative numbers seriously and taking complex numbers, numbers that involve the square root of -1, seriously. And for us, complex numbers are sort of a slightly more elaborate concept one doesn't learn about until one's doing, I don't know where one learns about it, maybe doing pre-calculus or something, whereas negative numbers are things everybody knows about. Cardano got involved with both of those because he was trying to solve cubic equations with x cubes in them, and that required both of those ideas. So let's see, a question here from Freeman. How do you do calculus on round objects like spheres or donuts? I'm not sure quite what do calculus means, but you know, so calculus, what is the idea of calculus? Okay, the basic idea of calculus is if you've got, let's say, something that is changing its value with time. So you can plot that as a graph. You could say, this thing is, it's going up, it's coming down, it's going up, it's coming down. I don't know, something like, well, in our current time, you know, number of infections measured by such and such a thing as a function of time, it has some curve. Okay, so we got this curve going as a function of time. Now, there are a couple of things that are interesting to do with that curve, and they're things which calculus talks a lot about. One is to find the slope of the curve at every point, and the other is to find the area under the curve. So let's talk about the slope of the curve. So let's say we have just a straight line going up. Then the slope of that curve is constant. So that we just say the slope of the curve is whatever it is. It's like when you're going down a hill or something in a car, and it says 15% gradient or something. That's the slope of the hill. For every 1 unit that you go along, you go 15% down or up. So that slope is just that ratio of the amount you go up to the amount you go across. So if it's just a flat line, just a straight line, then the slope is constant. Okay, so the next case is what happens if instead it's going up like a quadratic, like x squared. It's going up like this. Then what's the slope as a function of position? Turns out the slope gradually increases as you go further, and the amount it increases turns out to be proportional to how far along you've gone. So that's the sort of that's another typical result. Okay, so what's the calculus version of this? The slope is called the derivative of the well. Okay, so if we think about this thing, let's say as a function of time, we have some value as a function of time. Let's call it f of t, where t is time. So f is some function that tells us just how high it's going to be at a particular time. So then the derivative of f of t with respect to t is the slope of that curve that's defined by f of t. So derivative is just the slope of f of t, and there are rules about derivatives. So for example, if f of t is a constant times t, let's say a times t, then the derivative is just a. So that just means it's going in a straight line, and the straight line has slope a, then the derivative is just a. If f of t is t squared, a parabola, then the rule for taking derivatives says that the derivative of f of t is 2t. And in general, if the curve was t to the power n, the derivative would be n times t to the power n minus 1. Okay, so that's first big bucket of calculus has to do with finding slopes of curves. Okay, the other, and that's about differential calculus derivatives. The other big bucket of calculus has to do with integrals, and integrals are working out the area under the curve. So, for example, let's say we have just something that's completely flat, and we say, what's the area under this curve? Well, the area under the curve is going to be, if we start from the beginning, the area is going to be, well, that first rectangle plus the second plus the third plus whatever. The total area is going to increase linearly as we go across. So in other words, if we're finding the integral of if f of t is just a constant, then the integral of f of t is just t times that constant value. It's just the area of that sort of big rectangle made by whatever the value of f of t is, going for whatever distance you choose to go for. Well, then it turns out if you have something which has a straight line, then the integral, the area under that straight line, is a parabola. And in general, the thing you realize is that taking slopes and finding areas are inverses of each other. So in other words, if you find the area under this curve, and then you find the slope of the area under the curve, that's equal to the original curve. That's equal to the original function. So the slope of the integral of f of t, the derivative of the integral of f of t, is just f of t itself. And the same is true the other way around. If you work out the slope, and then you start aggregating it to find out the area under the function you get from the slope, you'll get back to the original function again. So derivatives and integrals are inverse functions. And the main sort of work of calculus, as people learn it in school, is knowing if you have a formula like, I don't know, x log x or something, to figure out what's the derivative of that as a function of x, and what's the integral of that as a function of x. And so you learn things like the integral of log x is x log x, I think, at least, minus x, actually. It's much easier to do derivatives than it is to do integrals. There's a completely systematic procedure for working out the derivative of anything. Basically, if you can write something as a function, f of g, of h, of x, then when you take the derivative of that, those functions kind of unpeel themselves, and it's easy to write down the answer. So derivatives are pretty systematic and easy to take. Integrals are a much more complicated story. I mentioned that integrals and derivatives are inverses of each other. So in a sense, when you're doing an integral, what you want to do is find a result such that if you took the derivative of that result, you get back to the original function again. And just knowing sort of how to shoot the right target to get the integral that to get that function, which when differentiated will give you the original thing again, that's tricky business. And when people learn calculus, that's one of the sort of difficult things to do. And it's something which, okay, so in Mathematica, Wolfram Alpha, and Wolfram language, we've kind of become the world's go-to place to get those kinds of things done. The way we do it is using a bunch of sort of sophisticated mathematical ideas which allow a very wide class of integrals to be computed, but not, even if you were taking the integral of, I don't know, x over sine x plus 1 or something. It's a slightly tricky integral to do. We would get the result for that integral in terms of some very elaborate mathematical function that people don't hear about in school typically. And then actually the main work is to simplify that very complicated mathematical function to something that people can recognize and understand. But the job of kind of working out analytically, working out as formulas, integrals, that's a tricky thing to do. And in general, there are all kinds of functions where, well, you know, if you say, what's the integral of okay, so I have kind of a mission to make here, which is that I started using computers to do math back when I was a mid-teenager, because I didn't kind of like doing all this math stuff by hand myself. And so I've been a person who's done many integrals in their life, essentially all on a computer. So if you ask me as a human to do integrals, I'm really crummy at it. When my older daughter was learning calculus, I think I annoyed her. She's now in the process of becoming a professional mathematician, but that's an independent footnote. I think I annoyed her by saying, you know, watching her do integrals by hand, I was like, I didn't think humans still did any of that kind of stuff, because I certainly haven't done it as a human for more than 40 years now. But in any case, so I'm a bad person to ask, you know, what's an integral of what? But I think I have to really think about it, you know, what the integral of these different functions is. Some integrals you can like just do systematically. Other integrals that seem like they're pretty simple functions are really hard to do, like the integral of sine of x. I know that integral can't be done in terms of ordinary functions that you would find in standard textbooks and so on. It can be done in terms of a very ornate bivariate hypergeometric function. But like sine of x, sort of three nested trigonometric functions, I think that integral cannot be done in terms of any ordinary mathematical functions that people have thought about. When I say it can't be done, I just mean there isn't a formula for what that integral is. If you just wanted to work out what's the value of that integral, taking that curve a certain distance, well, there'll be some number and you can work that out. Okay, so the original question was about doing calculus on spheres and donuts and things like that. What I've been describing is sort of ordinary so-called univariate calculus, single variable calculus, where it's just some function as a function of time or some function as a function of x and so on. But you can also do multivariate calculus, where you say, let's look not at a curve, but a whole surface. So let's say we look at the height as a function of position in the XY plane, and we've got some whole landscape, and we've got a big mountain there, and so on, and so on, and so on. And so then you can ask questions like, what's the generalization of the idea of slope for this whole like mountainscape? And that's a thing, instead of it being just a number, what the slope is, it's a direction and a number. It's a gradient vector. So for example, that would be, you're at the top of Mount Everest. Which way down is the one that is the fastest down? So it might be that some way it's a very shallow curve down the mountain, another way it's very steep. So what one does in multivariate calculus is often to find the gradient of this height function, and that gradient is a vector which points down the sort of steepest going down direction of the mountain, so to speak. And that's sort of the beginning of multivariate calculus. You can also consider integrals where you're working out not what is the area under the curve, but like what's the volume of the mountain, so to speak, or what's the volume of some figure, you know, some cone or something like this. Okay, so an even more elaborate thing is when you are looking at functions not just as a function of one variable, just a curve as a function of position, not just as a, you know, height as a function of position in the plane, but instead you're saying, I'm on the surface of a sphere, and now I'm going to have some function on the first surface of a sphere. So that will be like considering, you know, the mountains on the Earth, considering that the Earth is a sphere, or like you have a very small asteroid and you're asking for, you know, the height as a function of position around the asteroid. It gets a lot trickier because on the Earth, for example, the Earth is mostly a sphere, and we can just start talking about the height locally on the sphere. But if the whole thing is a really weird shape, it's a more complicated issue to define what you mean by height and so on. So there's a lot of results about calculus that apply to working out integrals and things like that over more complicated shapes. There's a bunch of very wonderful, beautiful mathematical results having to do with working out integrals of functions where the function is defined over the surface of, let's say, a sphere or a donut. And it turns out that certain kinds of results for certain integrals, the answer that you get depends only on the number of holes in the object. So a sphere is something which has genus 0, it has no holes in it. A donut, standard donut with a hole in the middle. It always confused me. When I was a kid in England, and I would sometimes read textbooks, and they were American textbooks, and they would talk about donuts, and they meant toruses. They meant things with, you know, with holes in the middle, with sort of circle around the outside and a hole in the middle. That always really confused me, because in England, at least at that time, a donut was a thing usually filled with jam that was just a blob of stuff. It didn't have any hole in the middle of it. So I couldn't understand what these sort of topological structures with holes in them were. But anyway, an American standard donut with one hole, that's a genus 1 object. And it turns out that one of the surprising things is that some of these results about calculus depend only on the number of holes. So if you had a 2-hole donut, you would get certain results and so on. It only depends on the number of holes. And there's a bunch of really nice mathematical results related to that, which I think, let me not get into describing those in detail here. All right, let's see. Another question here from All Ether. If you could change how we measure time, would you, and to what? Gosh, I'm not sure at what level we're talking about here. You know, it's a time goes by, we make certain somewhat arbitrary decisions about what the you know, how long is a second, how long is a minute, how long is an hour, how long is a day, how long is a week. Some of them are not so arbitrary. A day, we pretty much want to be more or less the time it takes the Earth to go around the sun, because that's a sort of a natural thing where we can say, well, you know, each day, each time we get up in the morning, each day we want something to happen. A year is also not so arbitrary, because it's roughly the time it takes the Earth to go around the sun. A month, well, there's a lunar month, the time it takes the moon to go around the Earth, that's about 28 days. We've chosen to make our standard in the standard calendar, we've chosen to make our months be 12 months, and they have this rather awkward stuff with some have 30 days, 31 days, etc. These are, so some the anchor points are more or less, a day is a day because that's the time it takes the Earth to go around. A year is a year roughly because it's some approximation to the time it takes the Earth to go around the sun. A month roughly the time it takes the phase of the moon to rotate or the moon to go around the Earth. A second, I suppose, is roughly one heartbeat. I don't know whether that's I don't know really whether that's where it came from, but that is something that's there. The idea of measuring time with 60 minutes in an hour, 24 hours in a day. Certainly 60 minutes an hour came from the Babylonians, who were very into base 60. Base 60 is really convenient because you can divide 60 into, if you want to say I'm measuring everything in 60ths, and how much, what I can have a half of a 60th, and that's still a whole number. I can have a quarter of a 60th, and that's still a whole number. And a quarter of a 60th is 15, like 15 minutes, a quarter of an hour type thing. So it's convenient to have 60 as the number of minutes an hour. If you want to divide an hour, like you're saying, quarter of an hour, it's still a whole number of minutes and so on. I think people occasionally, things like 7 days in a week. Well, that's something certainly existed. I think that existed in Babylonian times. I don't know, is that a good idea? Is that a bad idea? It's like if you want to really, I don't know how it would change society if we had 9-day weeks or 5-day weeks. I'm not sure. We might feel more relaxed. We might feel less relaxed. I don't really know. There are people who have these proposals occasionally to make 25 hours in a day. I'm not sure why we would do that. I think these questions about making it more convenient to calculate things, it's always worth remembering that now that we have computers, we can kind of calculate a way around anything. And it's not so. Sometimes it's convenient to be able to do sort of estimation of things. I tell a story about, maybe I told it on one of these before, but when I was growing up in England, the currency in England, money, was not decimal. So there were pounds, shillings, and pence, and there were 12 pennies in a shilling, and 20 shillings in a pound. And just for good measure, a guinea was 21 shillings. But in any case, so it was something where 12 pennies in a shilling, 20 shillings in a pound. So it wasn't a decimal currency. It's not like in the US where there are just 100 cents in each dollar and so on. And I remember telling some teacher when I was like probably 6 years old, I would guess, that I was very pleased with the fact that I'd figured out that money didn't have to work this way, that you could perfectly well have define prices for things in decimals. And this teacher was like, but it's been the way it is for 1,000 years. It's never going to change. And I was like, well, it's really silly. Well, then about a year or two later, it was announced that in fact, Britain was going to change to having decimal money. And that was going to happen in 1970. And so it was like, oh, okay, cool. But what was interesting to see was how confused or not people got with decimal money relative to having had 1,000 years or whatever of pounds, shillings, pence. And I remember that on television, for a year beforehand, they used to have these decimalization programs about, how to estimate money with decimal money, et cetera, et cetera, et cetera. And it was, I think nobody knew how confused people were going to be. As it turns out, it was interesting the day. I was 10 years old or something. It was the day when the money changed, and like you would hand in money in the old currency, and you get back money in new currency. And the most interesting thing to me was that people were not confused. That extremely quickly, people, were able to compute things just fine with decimal currency. And it wasn't like, oh, I'm so confused. I don't know, I don't know how to do this. Now, I don't know what's happened in more recent times. I haven't lived there for a long time. I know they went from measuring temperature in Fahrenheit to measuring temperature in Celsius. And I don't know how confusing that's been. My guess is not very. All right, next question here. Wow, okay, so there's a question here from Brian about that there are clouds of things like alcohols in space. And the question is, could there be sort of life that emerges from all of these lifelike molecules that exist in molecular clouds in space? Tough business. So most of what's out in, for example, interstellar space is mostly just hydrogen. That's it, just hydrogen. But there are some more complicated molecules. There are molecules that have carbon and hydrogen, some slightly longer hydrocarbon type molecules, some I think with oxygen as well. There are molecules out there that are some of the molecules that we find in living systems, not huge molecules like that, molecules that are, decent length carbon and hydrogen molecules. Those molecules arise in space by a process very different. It's not by chemical processes. In chemistry, when you do chemical reactions, molecules are being broken up, other molecules, other atoms, molecules are attaching themselves and so on. That's happening in the sort of, let's say in a liquid chemical reaction, that's happening when just molecules in the liquid run into each other and so on. In space, the process is in interstellar space, there just aren't very many molecules around. And so a common thing that happens is these molecules just sort of run into each other just in sort of free space. Two molecules will run into each other and then maybe they'll get attached. There are also interstellar grains, little tiny dust grains on which different kinds of reactions can happen. But they tend to be very different kinds of processes for building up molecules than the ones that you see in standard chemistry on Earth. So you build up sort of the set of molecules you build up is a different and somewhat exotic set of molecules. Can those molecules could you expect that those molecules would combine and make still more complicated molecules? Well, maybe, but not very fast. It's not like a chemical reaction on Earth where you could have this, beaker of liquids where they're just, trillions and trillions of molecules colliding all the time. In space, it's like, well, be glad if your molecules collide every 1,000 years or something. So it's a much slower process. Now, it's a very slippery slope to understand what counts as something being alive. Let me not get into that whole discussion. I think that the thing to say is can one expect that on a short time scale, things, just individual molecules hanging around in space will combine to make sort of the kind of collections of molecules that we're used to with life on Earth? That's a really long road. I mean, in the early Earth, a few billion years ago, things were really set up so that lots and lots of molecules were colliding all the time, and it was much easier to build up more complicated chemical processes and so on to make things that were the complicated molecules that have made life on Earth. I don't think that's the kind of thing we can expect to have happen in interstellar space. Question from Parmenides, a curious name given the question. Speaking of the Romans, do you think Latin is a better language than English for science and mathematics? Oh boy. Well, Latin is a very organized language. English is a language which is an amalgam of many different pieces from many different sources. And there are so many exceptions in English. In Latin, there are many fewer exceptions. I mean, when I was a kid learning Latin, a lot of what you learnt was the exceptions, the verbs that decline in a weird way. In English, it will be, I am, you are, he is, she is, whatever, we are, you are, they are. Okay, that wasn't so irregular, but in sum as est, sumus estus sunt, right? That's the Latin for that, and that's those are all sort of words that sound a bit different, but they all come together to be parts of inflecting the word for to be, present tense of the verb for to be. So English has just a ton more sort of unusual verb forms, unusual grammatical constructions and so on. I mean, as a good example of this, a Latin grammar book is a little thin thing. You can kind of learn it in a little while. Because I've been interested in natural language understanding for computers, I have, English grammar books that are fairly complete English grammar books, and they're big, thick, 1,000-page, 1,500-page documents, because English is so full of weird exceptions and so on. So Latin is a much more systematic language in many ways. It's also a language that, but it's a language that obviously didn't get to express a lot of things that are relevant for science and technology today. I actually have a friend who's a classics professor at Oxford University, and he has the curious job of doing the following thing. So at Oxford University, they give honorary degrees sometimes to distinguish people from different fields. And some of those people are people who do computer stuff or biochemistry or something like this. And at Oxford University, probably since the 1200s, they've had a tradition of explaining the achievements of their honorary degree recipients by a speech given in Latin. Well, the question is, if you're giving a speech in Latin, you have to describe the accomplishments of somebody who's worked on parallel computing or worked on the physics of antimatter or something like this. The question is, how do you describe that in Latin, given that the language of Latin is a language which has not been being added to in recent years. So my friend has the curious job of trying to make up the ways of explaining in a few words what a thing like a computer. I know he's got a word for a computer in Latin. I don't remember what it is, but that he uses for these speeches and so on. But obviously, you have to adapt Latin for modern times if you're going to do that. Now, in the history of these things, there was a time when Latin was really the language of scholarship, the language of intellectual work. I mean, I think that was probably the case from the time of the Roman Empire right up through, I would say, probably into the 1700s. And that was something partly driven by the Catholic Church and the dominance of that. But it extended to other places as well. That, if you wanted to explain something and you wanted it to have serious readership and it was an intellectual thing, you would write it in Latin. And that was probably a good thing because you didn't have to write in English and French and German and, in Spanish, whatever. All these languages as they emerged were all separate languages. But if you wanted to write your great scientific work, you just write in Latin, everybody would know how to read it. And that kind of survived up until, as I say, about the 1700s, when things started getting written in different languages. I mean, predominantly at that time, English, German, French, those were the most common languages. And really that continued until probably after the Second World War, when really English became the dominant language for scientific discourse. There's still a certain amount in French. France has been a country that's been very proudly trying to maintain its language, against the forces of corruption from words being imported from other places. And I think it's one of these languages where there's actually an institute that is trying to standardize the language and says, I don't know whether you can say le blockchain in French, but there'll be words which are like, no, you can't say that in French. It's not the right word. But in any case, when Latin was kind of on its way out, 1600s, early 1700s, as a universal language that actually drove a bunch of development. It actually was part of the impetus for mathematical notation, because there was sort of an idea, well, let's at least, even if we lose the language part of it, at least let's have the math be something that's internationalized. And people like Gottfried Leibniz were much involved in that effort. It's also led to the idea at that time of making what were called at that time philosophical languages which could express meaning, but without having specific words from particular languages. And sometimes those languages would get written in strange sort of runic scripts that was supposed to be something which is sort of a language-independent language, so to speak, that would express purely the meaning without the sort of the surface level of actual expression in terms of historically defined words in particular languages. That effort of making philosophical languages didn't really make it in the 1600s, and it kind of got put on the back burner for the last 300 years. Now, actually, I've been super interested in doing that, and in fact, our Wolfram language is kind of a run-up to being able to do that. It's a sort of computational language for describing the world, what I'm very interested in the idea of having a language that is a systematic language that can be understood by a computer that could express the kinds of things that I'm expressing to you now. We've obviously done a lot of work on this in things like Wolfram Alpha, where we're translating English into this sort of precise symbolic internal language that allows us to do computation. But I think now the idea of philosophical language, which was born out of this move from Latin in the 1600s and early 1700s, I think that idea, which has kind of not really been developed in the last 300 years, it's going to be one of my next projects to try and really develop that. It's something that's important for practical things in the world. It's important for if we write a legal contract that says, you know, person A must do whatever, this thing and that thing and the other thing, you have to write that in a way that's very well defined so that you don't have to argue about, well, did person A do what they said in the contract they should do, and so on. And traditionally, that's been written in basically, let's say, English or whatever native language one's using, and sort of legalese, which is an attempt to, you know, say things like, what's a good example? You know, the following, you know, conditions, including but not limited to the following conditions. You know, that phrase, including but not limited to, is basically saying there's a list of things, but there might be something else. And just because the thing that was the something else that was mentioned was what actually turned out to be important, you shouldn't ignore that, et cetera, et cetera, et cetera. But that phrase is a piece of sort of legalese that is an attempt to make more precise what would otherwise be expressed in English. If you have a sort of true symbolic discourse language, as I'm calling it, it's kind of a derivative of these philosophical languages. If you have a true thing like that, then you get to precisely define what you want to say. I mean, I might say there have been various attempts to make alternative natural languages for talking about things. I would say there was a big push on those things in the late 1800s, early 1900s. Most famous of those is Esperanto, which was a language which was intended to basically simplify a bunch of the standard European languages. And it lasted for a while, but it's not ever received a really huge following, partly, I think, in modern times, because English has been so successful as a language that a large number of people know. Let's see. Okay, oh boy, lots of questions. Okay, there's a clarification from Freeman here about the question about calculus on spheres and donuts and things. This is a question about sort of how you do calculus when you've got hills that are on the surface of the Earth, or worse, on the surface of a little asteroid. You know what? Let me punt on this question. That's a slightly complicated question because it'll lead us. Well, all right. I'll talk about it a little bit. Okay. So this is the question of how do we define. So here's a question: what's the tallest mountain in the world? Well, everybody knows it's Mount Everest. What does that mean? The tallest mountain in the world? Well, it means the tallest mountain relative to wherever the base is supposed to be. What is the base? Is the base sea level? What is sea level? So, for example, across the Panama Canal between the Atlantic and the Pacific, you would think, well, there's sea level, so the Atlantic and the Pacific must be at a definite level, but they're not. There are a bunch of locks in the Panama Canal. I forget which one is higher. I probably should be able to work it out. You know, the Atlantic and the Pacific, which both presumably are at sea level because they're both seas, so to speak, are not in fact at the same level. They're not at the same distance away from the center of the Earth. So the question of what's the tallest mountain is potentially quite tricky to define. one definition might be what's the mountain that's furthest away from the center of the Earth. Another might be what's the mountain, and by the way, that would lead you to very weird results, which I'll explain in a minute. Okay, so that might be one definition of tallest mountain, is the thing that's farthest away from the center of the Earth. Another would be what's the thing that's tallest relative to whatever you consider the surface of the Earth to be at that place on the Earth. Okay, why is that a tricky question? Okay, so first approximation, the Earth is a sphere, but it's not exactly a sphere. The Earth is rotating, obviously, once a day, and that rotation, even though the Earth is molten inside, but it's rock, it's a pretty solid kind of thing. The centrifugal force associated with the rotation of the Earth, the fact that like when you whirl something around, it tries to pull away from your hand. If you're whirling something around on a string or something, that force applied to the Earth causes the Earth to bulge out in the middle, so to speak. So the equator is bulging out. So the Earth is flattened. The poles are slightly, if you look at the distance between the North and South Pole, it's less than the distance across the Earth at the equator. So the Earth is bulging out at the equator. So if we say, what's the highest distance out relative to the center of the Earth? Well, it'll be something on the equator, because the Earth is bulging out at the equator. But so then how do you decide what is the surface of the Earth? What counts as the surface of the Earth? Well, it's a bit arbitrary, but the Earth is to a good approximation. It's not exactly a sphere, but it is pretty close to being an ellipsoid, the three-dimensional generalization of an ellipse. And so what ends up happening is that one defines, there are so-called datums which are defined, which are a particular choice of what ellipsoid one will be thinking that the Earth corresponds to. And okay, so this is getting a little tricky. So back in the late 1800s, there was a chap called George Everest, who was a person who was sort of surveying the Earth. And when he came to the Himalayas, he was looking around at mountains and things and trying to work out this question about sort of which mountain is highest relative to what you can consider the surface of the Earth to be according to this ellipsoid. And he had a particular ellipsoid that he used to define the surface of the Earth. And relative to that ellipsoid, he determined that this particular mountain was the tallest mountain. And I think I gather his family's frustration, the mountain, even though his name was pronounced Everest, the mountain became called Everest. But the determination that was the tallest mountain was a tricky thing. Now, okay, so then what happens? This is the field of study that's involved in this whole question about datums and so on, is a field called geodesy. And in geodesy, there are a variety of different datums that people use. And for example, it's very convenient to be able to say that North America, for example, which is essentially one tectonic plate, can be thought of as having one datum, one sort of effective piece of an ellipsoid. But that datum does not line up properly with the convenient datum to use for other parts of the world. When GPS became common, what is it called? WGS84, I think, is the datum that's used for GPS. GPS, because it's global to the whole Earth, you have this particular datum that is used it's an ellipsoid that is a good approximation to the ellipsoid for the whole Earth, even though the whole Earth isn't precisely an ellipsoid. So it's more convenient if you're just dealing with North America to pick a different effective ellipsoid for just the piece of North America. So what does this mean in practice? I remember years ago, I had a GPS and I was driving some car on a beach right by an ocean, right? And I'm looking at my GPS and I'm looking at the little thing you could press in those days. I'm not sure you can still do that on GPSs, but you get raw GPS coordinates and so on. And it said that I was 50 feet up. And it's like, I mean, I knew how this worked, so I wasn't as confused as I might have been. But it's like, how could I be 50 feet up? I'm right on the beach, right at sea level. The ocean is right here. How can I be 50 feet up? And the answer is because sea level is not the zero of the WGS84 datum that's used for GPS. So it's sort of a tricky thing. What is the zero, so to speak? And the different oceans are at different heights because the water in the ocean is for example pulled by the moon different amounts and so on. It's a question of and by the rotation of the Earth, the water bulges out different amounts and so on. So it's a tricky question, what the actual sort of zero of height on the Earth is. And so if you start asking questions like what's the you start asking sort of mathematical questions about working out, the total amount of, I don't know, even when you talk about sea level rise, even that's a tricky thing to define, what that really quite means relative to, relative to all these datums and relative to land and so on and so on and so on. I mean, things happen in geodesy. There are almost, I don't know whether a war has ever been fought over geodesy, but it's certainly come somewhat close, because there are things where people have defined, okay, there are also coordinate systems where people say, given this datum, I'm going to define coordinates to say where things are on the surface of the Earth. And for example, let's say there's an earthquake and the Earth actually moves. What do you do with the coordinate system? Or another case is you've got statements that my property consists of this thing where you go 1 mile in this direction, then you go east and you go half a mile in that direction, and so on and so on and so on. Okay, so people have defined those kinds of things. In particular, countries, when there are treaties between countries, or when people agree what the borders between countries are, they're usually written out in those terms. Go east this distance from the river, go this amount, et cetera, et cetera, et cetera. Where does that actually land up? Well, it can depend on these questions of geodesy. And sometimes it's very tricky. And I know there have been some cases where people have gotten very, very upset about, because it turns out that which way it goes depends on whether you get the oil or whether your neighboring country gets the oil, or you get the gold or your neighboring country gets the gold. So these things can be quite tricky. Okay. All right, let me see. Gosh. There's so many questions here. It's taking me a long time just to read through these questions. Okay, I'm going to take one that says, hello, I'm a kid and I have a question. How can one achieve, wow, this is something quite technical. How can one achieve file fragmentation in a file system designed for archive files? For example, how can one append X number of sectors to a static list of tar POSIX headers and file data sections? Well, okay, we can unpack that a little bit. Let me explain a little bit about that. It's a technology question. I'm not sure if I'm going to nail this particular question, but maybe it will be of interest to people. Okay, so you've got lots of files on your computer. Maybe I might have 10 million files on my computer. Maybe you have 100,000 files on your computer. Each one has a file name. It might be a .txt file. It might be a .jpeg image. It's all kinds of different files on your computer, okay? And those files on your computer are stored in your computer's file system. How do they actually get stored? And for example, so the file system of your computer might be an actual spinning disk. These days it's more likely a solid state disk. It's something where there is an address for every piece of data in that file system. And it's a linearly arranged address. So it goes from address number 1 to address number, let's say you have 100 gigabytes of storage, to address number, 100 billion, okay? So so what's happening is every piece of data, every byte of every file has to be put somewhere on the in that file system of your computer. Okay, so there's a tricky issue that comes up, and there are different ways to solve it. But here's the tricky issue. Let's say you've got 100 gigabytes of storage available. And let's say, well, let's make it simpler. Let's say you've got 1 gigabyte available, and you put in a 100 megabyte file. Okay, that takes a tenth of your 1 gigabyte of storage. Blump, it's put at storage locations, let's say 1 through 100 million. Okay, now you've got another file of a certain size, and you put that down somewhere else. But now the problem is that you can get this phenomenon called fragmentation, which is you've got these gaps, because each file, at least in the first way of doing this, has to be contiguous. Like all the bytes, all the pieces of data in that file have to live contiguously in your file system. So the locations in your file system are numbered, and it has to be the case that every piece of that file is just at successive places in your file system. So then the screwy thing can happen that, particularly when you create a file, you delete a file, you create a file, you delete a file, pretty soon you can end up with a situation where things are very fragmented, where you've allocated, you've got a certain amount of space that's been allocated, but there are, in principle, you've only allocated, let's say, 600 megabytes out of your 1 gigabyte of storage. But now you want to put in a 200 megabyte file. You say, well, that's no problem. It should fit. We've got 400 megabytes left. But no, the problem is you've not got 400 contiguous megabytes left. Your thing is broken up into all these different pieces, and there's no there's no contiguous sequence of locations in your file system that will be big enough to fit that 200 megabytes. So that gets very tricky. And there are a variety of solutions to this problem of fragmentation. Your operating system can move things around and remove that fragmentation and so on. There are a variety of schemes that are used, and I don't know the specifics of. I don't completely understand this question, so I can't really comment in more detail on it. I mean, I mentioned one other thing, perhaps of interest, about files. So let's say you got a file and it's full of text. It's your school essay. Well, the question is, let's say your school essay is, let's say 10,000 characters long, okay? Question is, do you need 10,000 bytes? Do you need 10,000 locations to store that 10,000 character essay? Well, it turns out you probably don't, because you can compress it a bit, because like every time you type to Q, there's a very high probability the next letter is going to be a U. And you can use that kind of information and the fact that different letters have different frequencies and so on to make an encoding of your file that is less long than the file itself. And so there are formats like zip and things like this that are archive formats that use compression to take sort of the redundant things like the U after Qs and things like that. Effectively, it's not really quite how it works, but it effectively takes those things out to compress things like English text. And with English text, you can usually achieve about 50% compression. So any piece of English text, if you run it through this compression algorithm, you'll get a file that's half as long, but the original English text can be recovered from that file. With images, depending on how accurately you want to reproduce the image and depending on how much fuzziness you allow, you can sometimes have much huger compressions, factors of 50, factors of 1,000. And eventually you just have to make a decision. How accurate do you want the image to be? Are you prepared to have the image? Do you want every single pixel to be right? Or do you, is it something where you're just trying to get something that visually looks more or less right? All right, so many different things here. There is a question here. I'm just about to hit my 1 hour mark. So many interesting questions. It's a question all right, I'm going to take a couple more here. Okay, first question is about protein folding. And do the things that we've studied have anything to say about that? Okay, so first of all, what is protein folding? What are proteins? Proteins are the molecules that we're pretty much made of. They are long molecules made up of sequences of blocks of atoms called amino acids. And your genome, your DNA, specifies how to make maybe 30 or 40,000 kinds of proteins. And they get made on demand to make, hair cells and to make blood cells and to make different kinds of things. That's what we're made of, is proteins, and inside each of our cells is the apparatus to construct each of these different possible proteins as specified from our genome. So one of the questions is, you've made this protein, it's made from a large number of units, let's say 1 million units of sequences of amino acids. Some proteins are millions long, some of them are thousands long, and so on. Different proteins are different lengths. But they're made from sequences of these blocks, of these there are 20 common building blocks, 20 kinds of amino acids that are used as the building blocks for proteins. Okay, so you've got this long chain of protein that's made, it's sort of extruded from the ribosomes inside your cells. When that protein needs to be made, it's constructed, and it's this long string. Okay, so you've got this long string of amino acids. The question then is, what does this long string do? And the answer is, the long string folds itself up, because there are attractions. Different amino acids are attracted to each other, repel each other, and so on. The string folds itself up. And that process of folding things up is both really important for living systems and really hard to compute. So the reason it's important, so there are proteins that don't really fold up much, that are long stringy proteins, like actin. The protein that's in our muscles is like that. It's a long stringy protein that is used to make the fibers in our muscles. There would be a protein like, hemoglobin. Hemoglobin is sort of a protein that makes kind of a cage, and it has a little gap in the middle of the cage that fits just one iron atom in it. And that iron atom is used to collect oxygen that's used to transport oxygen in our blood. Or a whole variety of different kinds of proteins. There are so-called globular proteins that are made, that look like big globs. There are proteins that have things called alpha helices, which are long sort of spirals. There are things called beta sheets. There are different kinds of shapes that show up in different proteins. Like, for example, a protein whose job is to transport molecules through the membrane of a cell. It might have an alpha helix, which is like a tube that's stuck through the membrane of the cell, and the ion, something like a potassium ion or something, or a sodium ion, might go through that tube, through the alpha helix of the protein, to get through the membrane of the cell. So proteins come in different shapes, and the shapes are very important for the function of the protein. But the question is, if you're just given, here's the sequence of amino acids in a protein, now tell me what shape this protein is, that's a very hard problem to solve. In nature, proteins do it pretty easily. They take seconds, maybe minutes, maybe, to fold themselves up. And pretty much, given a protein, pretty much folds itself up in a definite way. At least it does that if it's in water. It might not do the same folding if it was not in water, in some different solvent. And sometimes proteins misfold themselves. Sometimes they're supposed to fold this way, but actually they fold a different way. And it's possible that Alzheimer's disease has something to do with misfolding of proteins. And so protein folding matters, and protein folding in nature happens quite quickly. But it's been awfully difficult to figure out, to get computers to do accurate folding of proteins. And there have been two basic approaches. One is to just work out all the forces between the different atoms in the protein and try and compute, just solve this big system. It might require quantum mechanics, but you can pretty much ignore the quantum mechanics and just try and figure out what thing minimizes the energy by arranging these proteins, by arranging the amino acids in a different way. That's one, the so-called ab initio, from first principles approach to protein folding. The other way to do protein folding is just to say, well, we got a big database of proteins that have been folded, where we know how the thing is folded. Let's just use that database as training data and use that to learn how we think proteins will fold using something like machine learning. And there's been sort of there's every year there's a competition for who can do the best protein folding. And I think actually is a former employee of ours actually who is I think he won the competition this last year, but he's been working on the kind of the machine learning direction. And I think he finally has a scheme that uses machine learning and that wins the competition. But there's been this sort of neck and neck, you know, is it first principles, is it machine learning that lets you best predict how proteins will fold? This question about protein folding, one of the questions is, why is it a hard problem? That is related to questions about when there are, okay, so there are a class of problems about that come up with computers with defining problems where if you could guess the answer, you can check it's right pretty easily. But it can be really hard to guess the answer. And the many different tries you have to make, and there's nothing that really guides you into which guess to try to make. Factoring numbers is one that's probably like that. And protein folding has certain attributes that are like that, where if you can kind of guess the right arrangement to put the protein into, then you can verify that it has the lowest energy. But there are exponentially many. There are a huge number of different possible configurations that the protein can go into. And in principle, to find which one has the lowest energy, which one is the one that the protein will tend to go into. By the way, just to make it even more complicated, the protein doesn't necessarily go into the lowest energy state, because it matters what the sequence of foldings is. And at each step, it's going to go in nature into the thing that has certain energy minimization features, but it's not guaranteed that it finds the globally minimum energy. What really matters is what configuration it goes into in nature, because that's what determines the activity of the protein in a natural system, in a biological system. So it's a tricky thing, and there are it's complicated, and it's not there's still no really good solution. People have been working on this problem for at least 40 years now, and still difficult. It turns out there's some things that are easier, like RNA, for example. That's actually pretty easy to calculate the folding patterns for. Proteins are just a really nasty case. All right. There's one last question here I will try and address, though it's a kind of complicated one. It's from adenylyl cyclase, interesting name. Question is there a relation between the classification of finite simple groups and your physics theory? Well, the first answer is we don't know, but yet. But I'll just try and explain a little bit about what the classification of finite simple groups is all about. See if I can do this. Okay, so if you take an object, where have I got an object? Let's see, what object do I have here? Oh, here's a nice cubical object. Okay, so there's a cube. Okay, so if I have this cubical object, there are certain transformations I can make. Unfortunately, this isn't exactly a cube. Imagine this is exactly a cube. There's certain transformations that I can make on this object. I can turn it this way, I can rotate it this way, I could reflect it this way, and so on. There's certain transformations I can make on this object which will leave the object unchanged. You know, or leave, assuming this was a featureless cube, it didn't have anything in it, it didn't have anything written on it, we wouldn't be able to tell the difference between the cube in that orientation and the cube in that orientation, and so on. It would be something where those are symmetries of the cube. We're saying that there are a certain number of possible transformations we can make, which will lead us to an indistinguishable cube. Okay. Now, some of those transformations, we know certain properties of those transformations. Like if we have a transformation, let's say we just were looking at this, well, even if we're looking at a square, we can do this. We can take a transformation that rotates by 90 degrees. That transformation, if we apply it 4 times, we know we'll get back to exactly the same thing we started from. But these, and so we can ask about what are the different possible groups of transformations that have certain features, like, well, they have to obey certain properties. For example, every transformation, there has to be an inverse transformation. There has to be a transformation that does nothing. There has to be a property of associativity of transformations, which means if we do 2 transformations and then we do a third one, it's the same as doing one transformation and then doing two more. So with those properties, and those are true of transformations that we make on kind of regular objects, and that collection of transformations is called a mathematical group. And the question then is, if we just say, well, we've got the possible transformations of a cube, we've got the possible transformations of a square, we've got the possible transformations of an icosahedron, what possible sets of transformations are there that we can set up that have the properties that I described for a group: associativity, inverses, and existence of identity? So that question was, there are an infinite number of possible collections of such transformations, but they fall into certain definite families. And there was a big project in the 1970s and 1980s, particularly, to try and classify exactly what buckets of transformations that make groups there could be. And as I say, there's some infinite families, like you can have the group of any polygon, you can have a polygon with any number of sides. The group of the 117-sided polygon is different from the group of the 118-sided polygon. You can do that for any size of polygon. It's a cyclic group of order n. Actually, it's not just the cyclic group. There's a little bit more to it than just the cyclic group because of reflections. But anyway, so in any case, you can classify these different possible transformations that you can make. Well, so there's a big project to try and find what are all the families of different transformations. Some of them are very straightforward families, like they're associated with polygons of different number of sizes, but there's some very exotic ones. And there's a particularly exotic one. There's a sequence of really exotic ones, and that is a finite sequence. It ends in this thing called the monster group, which is this group of transformations that has a huge number of elements. I forget how many. It's in the trillions at least, maybe more than that, maybe trillions, I'm not sure, of possible transformations that are not transformations of anything that we are familiar with, like cubes and things like that. It's transformations of some giant mathematical object. But that set of transformations, it has a certain degree of elegance because it is the exceptional, the only, the last, the biggest sort of exotic, special finite group. So that group has many interesting properties, and many things that are important in mathematics turn out to be subcases of that group. And so it is possible that in our theories of physics, that in particular that there may be some things which are effectively coming out from something like the monster group, this biggest group. It's a little bit tricky because there are not just finite groups, there are also infinite groups which have an infinite number of transformations in them. And there are also things called Lie groups, L-I-E groups, that named after a chap called Sophus Lie, who was Norwegian. The Lie groups are groups that have a continuous set of possible transformations. They're kind of the analog of calculus for groups, where one has not just a discrete set, we can rotate the square by 90 degrees, but you can rotate the object like a circle by any angle, however small that angle is. The symmetry group of the circle is a Lie group, a continuous group. It's called U1, the group of the circle, and that's another kind of group. And in trying to make contact with physics, most likely what's going to be relevant is Lie groups. And in fact, in our models of physics, which are discrete models of physics, which have only just this sort of this Lie group arises as a continuous, as a limit of a very large sized object, and how that limit works is you're sort of taking the limit of if you have enough. It's like the limit of if you have enough molecules in your water, the water will seem continuous. If you have enough sides in your polygon, the polygon will seem like a continuous circle, and that's the way in which we get these kind of Lie group type things. But it's conceivable that in the way from our discrete system through to something like the Lie groups that correspond to the so-called gauge groups that are fundamental to particle physics, that we'll end up going through this monster group. All right, I think I should wrap up there. Thank you very much for lots of interesting questions. I'm sorry I didn't get to everybody's question today. Please drop in again next week, and I will try and get to some more of these questions. Thanks a lot. Bye for now.